If we were to compare the Earth to an ordinary chicken egg, then its crust is 20 times thinner than the shell relative to its diameter. Just imagine what would happen to such an egg even in the gentlest hands. In 2016, a group of American scientists found that the crust beneath the oceans became thinner by 1.06 miles, or about 1.7 kilometers. What's the reason for this change? And what threatens humanity with the continuation of this process? Don't worry, it's still too early to panic and start planning how to colonize neighboring planets today. Geological processes are not quick, and nothing deep in the Earth's interior, nor on the surface, changes in the blink of an eye. For example, the thinning began about 170 million years ago, when modern continents were still merged into a single supercontinent, Pangaea. But even then, it gradually disintegrated into separate fragments caused by the movement of the lithospheric plates, just like other supercontinents before it. Why is the surface of the Earth so changing? To understand all of this, scientists track changes in the outer layer of the Earth over the past 2.5 billion years, analyzing 234 measurements of the thickness of the Earth's crust around the world over a number of geological eras. For starters, we'll dig even deeper and look under the crust. There is oozing mantle. However, oozing is not exactly the right word. The mantle, with the exception of a few places, is a layer of hot, solid rock that occupies about half the Earth's depth and more than 80% of its total volume. Like the outer coating around the nut in a praline, it wraps around the core of the Earth and always remains hot. Most of this heat has been preserved since the formation of our planet about 4.5 billion years ago, when, according to one theory, it was covered by a fiery ocean of magma. Since its solidification, the mantle has moved very slowly, but it continues to move to this day due to so-called thermal convection. This process is common and can be seen even in a cup of coffee. In relation to the mantle, this means that the rocks located closer to the Earth's surface become cooler and heavier, and they sink, while the rocks in the lower part of the mantle, near the red-hot core, rise because they're hotter and lighter. This happens despite the typical rule that only a fluid substance can move in this way under the force of gravity. So then, how is this possible with the solid mantle? The answer can be clearly illustrated by the example of a jar filled with balls tightly packed next to each other. If the jar is tilted enough, the balls will begin to leave their recesses and move to new places following the tilt of the container. That is, the layer of balls flows from one place to another while remaining solid. Of course, the mantle moves much slower than in our example, and yet this movement is incredibly important for the Earth. It's convection that sets the slow pace of cooling for our planet. This process transfers heat to space. That is, it maintains a stable climate suitable for life. It also creates the movement of lithospheric plates and the related geologic processes. The first gift that this convection gave to the planet was the appearance of a magnetic field that protects the atmosphere and all inhabitants of the Earth from solar cosmic rays and solar wind. Another, no less valuable gift was the thin crust of the Earth, which was formed by the lightest substances that rose from deep inside the Earth. True, little has survived from the original shell to this day. In some parts, it became thicker over time, thereby laying the foundation for the continents, a process which took about 2 billion years. But the Earth's crust isn't uniform. There are continents with a thickness reaching up to 49.7 miles, or about 80 kilometers, under mountain ranges, and oceanic crust, which in places can be 10 times thinner. It's in this second area of the crust that there's a thinning that has attracted the attention of scientists. A new oceanic crust is formed due to the emergence of hot rocks on the surface in the areas around fault lines. Moreover, its thickness is directly dependent on the temperature of the mantle substance. The higher the temperature, the thicker the layer is when solidified. The study revealed two interesting things. First, the planet today produces much less magma than during the time of the dinosaurs. Second, the mantle, as a result of convection, cools much faster. So, 2.5 billion years ago, the mantle cooled at a rate of between 42.8 to 51.8 degrees Fahrenheit, or between about 6 to 11 Celsius, every 100 million years. But then, 170 million years ago, some geological event occurred that accelerated the process. And since then, it's cooled at a rate of 68 degrees Fahrenheit or 20 degrees Celsius. Despite the fact that scientists expected a decrease in the temperature of the mantle with time, since the heat that remained from the moment of the Earth's formation and received during the decay of radioactive elements dissipates, this speed surprised them. The Earth seems to be cooling much faster than at any time in its entire history, said geophysicist Van Avondonk of the University of Texas. It's important to clarify that this can't happen to a climate that isn't cooling. So, what happened in the middle of the Jurassic period when the rate of cooling almost doubled? And how is Pangaea connected to this? The fact that it split into separate continents entailed one of the largest changes in lithospheric plates. Apparently, when the continents began to move away from each other, the deeper layers of the mantle were exposed to the atmosphere and the ocean. Then it began to cool much faster, while the temperature of the mantle beneath the Pacific Ocean decreased by about 55.4 degrees Fahrenheit or 13 degrees Celsius over 100 million years. The mantle beneath the Indian and Atlantic Oceans became colder by about 98.6 Fahrenheit or 37 Celsius during the same period. This difference is likely related to the distance between the continents. As a result, the thickness of the crust beneath the Pacific Ocean has decreased to a slightly lesser extent. So, rearrangements of lithospheric plates led to temperature changes in the mantle. As a result, the oceanic crust began to solidify in a thinner layer. From all of this, a logical question arises. What caused the breakup of Pangaea? Researchers believe that the heat accumulated beneath it at one key moment, of course, that is, a moment by geological standards, broke through and divided the land into parts. All these discoveries make you think about how such processes will affect humanity in the future. Most likely not at all, because by the time they begin to pose a mortal threat, there will be no more people left on Earth. This is because of the Earth's core. Now, the slow cooling of the mantle does not allow it to cool too quickly, and it's still mostly in a molten state. But, according to various estimates, in about 1 to 2.3 billion years, it will finally cool down. This will lead to irreversible changes, the main one of which is the planet's loss of its magnetic field. Today's cold and deserted Mars also once lost its global magnetic field after a collision with a massive space object, and with it lost its protection against solar radiation. By analogy, we can imagine the consequences for the Earth. Our magnetic field is extremely strong for such a small planet. In shape, it looks like a whale with a long tail, thanks to the solar wind flowing around it. If this whale disappears, the ozone layer will also disappear. But even if you exclude the extreme case of the complete destruction of the magnetic field, just its weakening will mean trouble. Compasses and equipment across the Earth will start to fail, and people will suffer from skin diseases caused by increased ultraviolet radiation. The cooling of the core will also affect the tectonic processes. They'll stop, and the activity of volcanoes will cease. But the movement of lithospheric plates, among other things, saves the Earth from the greenhouse effect. Organisms, when they die, emit carbon dioxide. If it's not absorbed by the Earth, this will lead to the accumulation of a critical mass of this gas. But back to the present. The thinning of the Earth's crust as opposed to the dangers that are in the distant future, is happening now and can lead to powerful eruptions of previously hidden volcanoes. Magma will begin to erupt to the surface through weak places. They are most active in the so-called subduction zones. In these places, one tectonic plate goes under another as a result of a collision. This is where the most destructive earthquakes occur, which pose no less danger to people. Thus, despite the similarity of their shape, different fates await the Earth and the egg caused by the thinning of its shell. Reducing the thickness of the Earth's crust doesn't lead to global rupture and leakage of all its contents. If you like the video, give it a thumbs up, subscribe to the channel, click on the bell to enable notifications of new videos, and don't forget to recommend us to your friends.